Okay, here we go. Let's talk about how to perform operations with matrices. Now, there's a few more terms that we need to either review or learn. So let's just refresh ourselves on what a matrix is and the different parts of a matrix. So if I have a matrix, again, it's just a rectangular array of data. Each of these inside the matrix are elements or entries of the matrix. And the way you want to label them, let's say, so if I'm looking at this, I see that I have 2 rows, and I have 1, 2, 3 columns. So what would the order of this matrix be? The dimensions of this. This, again, we always label it as the number of rows by the number of columns. So this is a 2 by 3 matrix. Each of these is elements, and if you notice, there's a little subscript. Now that little subscript is kind of telling you the location. The first number, which I'm just calling I, is the row number. The second number, J, is the column number. So that's not an 11. That is element A in the 1, 1 position. This would be the element in the 1, 2 position. First row, second column. First row, third column. Second row, first column. Second row, second column. Second row, third column. So we can identify the elements, the specific element I'm interested in, by labeling it, and those subscripts, again, the first number is the row, the second number is the column number. So let's say I give you this matrix A, and I ask you, what is the entry in the 2, 1 position? So that's the second row, first column. Second row, first column. You would say it's -2. Right? So what if I ask you what is in the 1, 2 position? What would you say? 2. What is in the 3, 1 position? It does not exist, right? There is no third row. So be careful, right? Row number is first. Now, there's some special matrices, and we should be able to identify them. If I have only 1 row, so this is just 1 row, it may have columns, but just 1 row, I call that a row matrix. And what are its dimensions? What is the order of this matrix A? It is a 1 by 4. Now, I can also have a matrix that has only 1 column. Guess what? That's called a column matrix. And what is this order? 2 by 1. 2 rows, 1 column. Be careful. Okay? If I have the same number of rows as columns, do we remember what we call that? A square matrix. And what is the order of that matrix A? 3 by 3. And if I have a matrix that has all zeros, this is called the zero matrix. Matrix of all zeros as its elements. And the order of that matrix? 2 by 2. So this is also a square matrix, right? Since the number of rows equals the numbers of columns. Yes. Wait for it. Wait for it. Just wait for it, right? Because remember, there's properties where we have to look at additive inverses to get the zero matrix, right? So, I mean, you know, it serves its purpose just like 0 in the world serves a purpose. But good question, Josh. All right. If we refer to entries that hold the same position in 2 or more different matrices, we would call those entries corresponding entries. So if I were to look at matrix B and matrix C, they're each square 2 by 2 matrices. But if I look at element B21, that's in the second row, first column, that corresponds to C21, which is also in the second row, first column. Now, we say that these two, so these are corresponding entries, and if the corresponding entries, all of the corresponding entries are equal, then we say that the two matrices are equal. So matrices are equal, oops, if and only if their corresponding entries are equal. So are B and C equal? Yes, they are. So they may be represented in equivalent values, but those values have equal values. Now, if I look at the next example and I say, determine if these are true or false statements, well, the first thing you want to do is, well, let's label the order of this first matrix. What is the order of this first matrix? 2 by 2. And the one on the right-hand side of the equation? 2 by 2. So if they're not the same order, they can't be equivalent, because then they don't have even corresponding entries that exist. So are these two equal? No, this is false. And I can tell immediately, because if I compare the 1, 1 position, they're not equal. So done. If one's not equal, then they're not equal in the corresponding entries. Okay, what is the order of the first matrix in the next example? 2 by 3. And what about the right-hand side of the equation? 3 by 2. So, could these be equal? No, because they don't even have corresponding entries for all entries. So these have different dimensions. So in particular, okay, so they both have 1, 1. They both have 1, 2. But look here, this has a 1, 3. It doesn't exist here. This one has a 3, 1. You see how they can't possibly be equal? So in this case, corresponding entries are not equal. In this case, they have different dimensions, so forget it. Now, let's look at the next one. The next one, I'm telling you that these two matrices are equal. So if these two matrices are equal, I know their corresponding entries are equal. So I know this 1, 1 and this 1, 1 position are equal. I know the 1, 2 position is equal. I know the 2, 1 positions are equal. And I know that the 2, 2 positions are equal. I'm telling you these are equal. And so then you'd have to go and determine for what values of X and Y would make this true, would make these two matrices true. Well, all you'd have to do is take the corresponding entries and equate them. So do you see how I took the 1, 1 here and that's equal to the 1, 1 there? Okay, so what would X equal? 4. And I would do the same thing with the other set of corresponding entries. Here I have the 1, 1 position, the 1, 1 position. And so this is true if Y equals -10. So you would say that this is true when X equals 4 and Y equals -10. Bless you. Okay, so that's when we have equal matrices. And that's what it means to look at corresponding entries. Now, let's talk about how we're going to add and subtract matrices. So I have two matrices, and I want to add or subtract them. You can add or subtract two matrices if and only if they have the same order. Now notice, these are the rules for adding and subtracting. These are not necessarily the rules for any other operation. These are the rules for adding and subtracting. To add or subtract matrices, they have to have the same order. Why? Because all you do is perform that addition or subtraction on the corresponding entries. So I have given you 4 matrices, and I'm asking you to perform these 4 operations if possible, and if not possible to perform this addition or subtraction, explain why. So let's look at the first one. The first one is saying take W. So there's W. W is 3, -2, 1, 0. And it's asking you if you can add it to Y. Y being 1, 4, -2, 3. So what do you think is the first thing that you want to check in performing this addition? Make sure they're the same order, because if not, there's your answer. First matrix has what order? 2 by 2. Second matrix has what order? 2 by 2. So can I add these together? Absolutely. And the resulting matrix itself is also going to be a 2 by 2 matrix. So if I perform the operations, I do it element-wise. I'm going to add the corresponding entries. So 3 plus 1, 4. What about the 1, 2 position? What about the 2, 1 position? -1. What about the 2, 2 position? 3. So I can add those 2 matrices. Now let's look at the next operation that you're being asked to perform. It's saying take matrix X let me write it, and it's saying subtract matrix Z. What is the first thing I want to check? Check the order. Can we do this? The order of the first matrix is what? 2 by 3. The order of the second matrix is? Can I perform this subtraction of matrices? Yes, my result is also going to be order 2 by 3. What is in the 1, 1 position? 4 minus 2, 2. Keep going, read it row-wise. Fantastic, okay? Now, let's look at the next example. It's saying take matrix X and add matrix Y. It's not possible. How come? Beautiful. So this is 2 by 3. This is 2 by 2. And you'd say cannot add or perform the addition, cannot add matrices because they are of different order. Do you have to state that exactly like that? No, cannot perform addition because the matrices have different orders, something along those lines. But you'd have to explain to me why that operation is not defined. Okay, let's look at the next one. We're being asked to start with matrix Z, oops, and subtract, oh, boy, I have an issue switching back and forth, Y. Different orders, okay? So this one is a 2 by 3, this is a 2 by 2. So again, I'd have to state, cannot subtract or perform subtraction because matrices have different orders. Now, this is important because as we learn how to do other types of operations, there's going to be different reasons why you cannot perform the operation. So you have to be very, very explicit in explaining the reason why you can't perform that operation. Okay, now we talked about how to add and subtract matrices. Now let's talk about how to perform matrix scalar multiplication. So when you're working with matrices, if you have a number that is just a real number, it is also known as a scalar. A scalar is just a real number. Now, if I want to perform matrix scalar multiplication, I want to multiply a matrix by a scalar, the product, meaning taking the multiplying, the product of a scalar, and I'm saying the scalar, let it be C, and the matrix, let's call the matrix A, it is known as the scalar product. So matrix scalar multiplication results in a scalar product. You can multiply every entry in the matrix A by that scalar. Okay, so let's look at an example. I have 3 matrices, P, Q, and R. For kicks, let's go ahead and state the orders of each of these matrices. Matrix P is a what order matrix? 3 by 2. What about Q? 2 by 3. And what about R? 3 by 2. So if you were being asked to add or subtract, what are the only 2 matrices that have corresponding entries for all elements? P and R. So that's that rule, right? But we're performing matrix scalar multiplication first. Okay, so let's take a look at the first operation that you're being asked to do. You are being asked to multiply scalar 3 by matrix P. Matrix P, I'm going to put in here 3, -2, 1, 0, 2, -1. And then once I perform that operation, because, you know, order of operations, right? Please excuse my dear, we do multiplication before we do subtraction. Then I'm going to subtract Q. So let's talk about the scalar multiplication first. If I were to perform this scalar product, a matrix times a scalar, I am just distributing this 3 by multiplication to each of these elements. So what would that yield? Okay, now the next thing you're being asked to do is this. And what would you, how would you respond to that? Right, so here we can perform scalar matrix multiplication. You wouldn't necessarily have to say that because you will have done that. But then once you get to this point, you would say can't subtract Because matrices have different orders, different dimensions. Yeah, you'd have to stop there. That's as far as you can go. That's as far as you can go. Okay, let's look at the next one. You're being asked to do scalar matrix multiplication first. Okay, and then R is going to be 1, 4, negative 2, 3, 0, 4. And then you're being asked to subtract P. Okay, so let's perform the scalar multiplication first. Scalar multiplication yields me what matrix? No. 3 times 1 is 3. 3 times 4 is 12. Keep going. Yes. And now what do I have to do? I have to subtract. Can I perform subtraction? What is the order of the resulting matrix? Okay, very good. All right, and give me those elements. Yes. So that would be my final answer. We good with addition, subtraction, and matrix scalar multiplication? Good. Now, what if I embed these operations in an equation? So I have an equation that involves matrices. You are being asked to solve for this matrix X given this equation. So I'm trying to find the matrix X, but I know matrix A and I know matrix B. So all I'm going to do is substitute in what I know into this equation. So it's going to be 4 times matrix X, which I don't know, plus matrix A, and that is going to equal matrix B. Now, at this point, do you know what the dimensions, the order of matrix X is? You don't? X has to be a 2 by 2 matrix or else I wouldn't be able to add those matrices together, right? So good. Now, I'm going to approach this like I would solve any equation. I'm going to try to isolate the X the best that I can. So what do you think you might want to do first? Okay, so I'm going to subtract this matrix from both sides. You are absolutely correct. Okay, so that's going to give me 4 times matrix X, which I am solving for. And if I perform subtraction element-wise, corresponding entries, what is my new right-hand side going to be? Yes. Now, I still have a coefficient, a scalar product on the left. 4 times X. If I want to isolate the X, what can I do with that 4? I can divide both sides by 4, right? Or multiply by a 4th, right? It doesn't matter. I'm going to stay scalar multiplication here, multiply by the inverse, because then I can come over here and do the same thing, right? And that's easier to look at. So what am I really doing? Well, I'm multiplying each element by a 4th, but I'm dividing each element by 4, right? That gives me, do you see how we're doing that? So X equals, take each of those entries and divide them by 4. What is X? Beautiful. Can everybody see how we solve for X? Okay, let's try another one because these are fun. Okay. Let me substitute in what I know. Negative 2 times, well, I'm solving for x minus a equals b. I'm solving for x. Now, obviously, I could have taken this x and substituted it back into my original equation and make sure I get a true statement, right? So there's really no reason for you to miss these because you can always check them, right? All right, what do I do first? Add what? Mm-hmm. Okay, so I have negative 2x equals what's on the right-hand side? So far, so good? Now, I need to address this. So what can I do to both sides to isolate that matrix X on the left? Yes. So in essence, I'm dividing each one of those elements by 2. So that means X is what matrix? Negative 3 over 4, right? You should be able to perform those operations. All right. Here we go. You ready for matrix multiplication? This gets out of control, but it's beautiful. Once you do it a few times, it's not bad. The first time you see it, you need to just take a deep breath. Huh? We were doing scalar matrix multiplication, a little real number times a matrix. Now we're multiplying two matrices, two matrices multiplied by each other. It's a lot more exciting, yes. It is more exciting. Yes, you do. Get excited. Here we go. Here we go. Okay. If A, and again, order matters. Let's look at this. If A is an M by N, so it has M rows, N columns, right? If A is an M by N matrix and B is an N by P matrix, so N rows, P columns, the product, AB, the product, AB, is going to be an M by P matrix. Now let's talk about how we know that. And let's talk about the condition that has to be satisfied for us to even be able to perform this multiplication. So for us to be able to multiply matrices, the number of columns in the first matrix must equal the number of rows in the second matrix. The number of columns in the first matrix has to equal the number of rows in the second matrix. These two have to be the same value. Okay? I like to write the order underneath and then compare those two little inner numbers. Okay? If these two numbers are not the same, if the number of rows in the first matrix doesn't equal the number of rows in the second matrix, this matrix multiplication is not defined. You cannot multiply those matrices. Now, how am I determining what the result is going to have as its order? Is looking at those. So the product, its order is the same as those outside indices. So these are going to give me the order of the resulting matrix. These must be the same for me to even perform the operation. So let's look at a few examples. Let's say you've been given these 4 sets of matrices and you're trying to determine if you can even multiply them. I'm telling you that the first matrix is a 3 by 3 matrix. The second matrix is a 3 by 2 matrix. Can I multiply these two together? These two numbers are the same, and the order of the product of these two matrices will be what? 3 by 2. Let's look at the next example. Can I multiply a 1 by 3 by a 2 by 3? No, I'm looking at these and they are not the same, so I cannot perform matrix multiplication because the number of columns in the first matrix does not equal the number of rows in the second matrix, and you have to explain that explicitly. You see how that differs from the reason why you would not be able to add or subtract. Okay, what about the next example? Can I perform matrix multiplication on these two matrices in this order? No, again, these are not the same, so I would use the same justification. But you have to explain why you can't perform it. What about the next example? Can I perform matrix multiplication on these two matrices in this order? Yes, I can, because the number of columns in the first matrix equals the number of rows in the second matrix. The resulting matrix is going to have what order? It is going to be a 3 by 5. Okay, so first thing you want to do is say, can I even multiply them? If I can, the next thing you want to determine is the order of the product matrix, the matrix product. That is going to help you remember how to multiply matrices. So here we go. Here we go. This is exciting. So exciting. Okay. You have been given two matrices. Let's explore the order of each. A is of what order? B is of what order? Can I multiply these two matrices together? Yes, since these two numbers are the same, I can multiply. What is the order of the product? It is going to be a 2 by 2 matrix. Okay, so the first thing that you want to do, until you get a hang of this, the first thing you want to do is you want to write the order of the resulting matrix. Okay, I know AB is 2 by 2. Now, just as a little reminder, let's label those entries in terms of their row and column. Let's talk about those subscripts. What was the subscript for the first element? Row 1, column 1. The second element, row 1, column 2. The next element, second row, first column. The last element, 2, 2. Now, the reason I'm writing this out for now is because those little subscripts are basically telling you what parts of the original matrices am I looking at to start multiplying? Okay, this one is 1, 1. So whatever I end up putting here is the result of doing some stuff that we're going to talk about to the first row of A and the first column of B. This is A. Oops. This is A. This is B. So to get this 1, 1 position, I am looking at the first row of A, the first row of B. Before I talk about how we're getting that number, let's just make sure we understand. For the 1, 2 position, I am looking at the first row of A, but the second column of B. For the next one, for this 2, 1 position, whatever goes in the final matrix, it's a result of looking at the second row of A, but the first column of B. And again, we'll talk about how to get these numbers, but I want to make sure that you understand what we're looking at to begin with in the pattern. I'm trying to establish a pattern for you. To get the 2, 2 position in our final matrix, I'm looking at the second row of A, the second row of B. So again, to reiterate, to get this final answer, 1, 1. To get this answer, 1, 2. To get this value, 2, 1. To get this value, 2, 2. So do you see how I'm reading it? And that's why it is very helpful to understand that these are telling you what to look at in your matrix product. Now, I know what to look at, but what do I do with those elements? Well, to get this 1, 1 position element, I know I'm looking at the first row, the first column. I am looking at first, well, let me circle it and not highlight it. 0 times 5 plus 4 times -2 plus 9 times 6. So I'm taking entry by entry from each matrix. After I've figured out which parts I'm looking at, I'm taking the product of those two entries and adding them, adding all those products. So this is 0 minus 8 plus 54 gives me the 46 in the 1, 1 position. I now have the 1, 1 position in my product. Now let's do the same process, but let's now look at for the 1, 2 position. First row, second column. Multiply, 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 add those products. 0 plus 28 plus 0 gives me that 28. Here we go. To get the 2, 1 position, multiply, 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 add those products. And last but not least, to get the A2, 2 position, second row, second column, multiply, 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 and add. Now, yes, this is cumbersome, but But again, once you establish a little pattern, it multiply. I mean, it becomes very routine after you've done a few. Josh, question? Well, you answer that question to me. Okay, so you're telling me that you want to be able to add a matrix of the same order, 2 by 2 times a 2 by 2. Can I multiply matrices of the same order? They'd have to be square, right? Because if those are the same, I gave you a special case, right? These two are the same, the result is a 2 by 2. But as you've just mentioned, if I had a 2 by 3 and a 2 by 3, these are not the same, so you cannot multiply. Good question, right? The number of columns in the first matrix has to equal the number of rows in the second matrix. The order of the product is the number of rows in the first matrix, the number of columns in the second matrix. All right. Shall we do some together? Yes, here we go. It's not bad. You just have to practice it. That's okay. Okay, so what might we want to do first? Write the order of everything you're working with. Okay, so the order of A is what? Sorry, yes. Let me do it down below. This is a 3 by 2. B is a 2 by 2. Can I add them? Yes, these numbers are the same, so I'm good. But what is my resulting matrix going to be? It is going to be a 3 by 2. So again, I like to write the whole everything down. So I'm going to write A because I now know that this can be done. Let's go ahead and write down everything. There's A. There's B. And I know, and I make this really big on purpose. This is a 3 by 2. 3 rows, 2 columns. I'm going to show as much as I can here to help you. Okay, so if I want to start by finding this, what position is that? 1, 1. First row, first column. So that's going to be -2 times -1 plus 3 times -2. So that's going to give me, let me turn this sideways because we may need some space here. Okay, so in my final matrix, and I draw these lines. I mean, I like to see it. You can draw those. If those help you, draw them. So if I perform that, that's going to be 2 minus 6. So what is the result in your matrix product, your final matrix? Yes. Okay. Now, I want to figure out what I am multiplying to get this entry. What position is that? 1, 2. First row, second column. -2 times 3 plus 3 times 4. -6 plus 12 is 6. Okay, now let's move on to this. What position is this? 2, 1. Second row, first column. 1 times -1 plus -4 times 4. Perform those operations and what goes in the 2, 1 position? 7. Oh, no, sorry, that's a 2. That's a 2. Okay, let's keep going. What position is this? 2, 2. Second row, second column. So that's 1 times 3 plus -4 times 4. So what goes in the 2, 2 position in our final matrix? Cover your nose. Yes. Okay, let's keep going. What position is this? 3, 1. Third row, first column. -6. And then this is what position? Third row, second column. Which would give me, and I'm done. So do you see this? 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2. I mean, you're just going through all the elements, all the positions. Okay, let's try the next example. What is the order of B? What did we say? It was a 2 by 2. What is A? What do you say? Yes. And you better believe you are going to be asked to justify any operation that you cannot complete. Okay, let's try the next one. What type of matrix is matrix A? It is a 1 by 3, and how would I call? Well, how would I label that? What name is it? What kind of matrix? It has a special name. It's a row matrix, right? And matrix B is what? It's a 3 by 1. It is a column matrix, so we need to know those. Can I multiply these two together? Yes, these two numbers are the same, and what is that going to give me? A 1 by 1. Oh, I just get a scalar. Well, isn't that interesting? Let's see how that works. I know I get a little scalar. And what position is that? First row, first column. So how do you think I'm going to get that? Yeah, I'm just going to say 1 times 3 plus 4 times -4 plus -2 times 5. So what is my scalar result? And I'm done. It's a little 1 by 1 matrix. You don't have to even put it in a matrix because it's just a scalar. But we're talking about matrices, we put it in matrix form. Okay, let's try the next one. B is, we said 1 by 1. No, I'm sorry, 3 by 1. A is 1 by 3. I can multiply because these are the same, but my resulting matrix is going to be what order? Ooh, 3 by 3. So let's write those. Okay, so in this, it's what position for the first element? It's what position? First row, first column. So 3 times 1 is 3. Okay, what about the next one? Well, the next one is what position? 1 by 2, first row, second column. So what is that going to give me? And can we keep going? You think y'all can keep going? Excellent. And there's your answer. Yes. Yes, I don't care. If it helps you, by all means, do it. Now, this is very interesting because this is telling us something. What is this telling us? We should recognize that a certain property doesn't hold. Does it matter the order in which we multiply these matrices? Yeah, the commutative property for multiplication doesn't hold for matrix. We just showed that AB doesn't necessarily equal BA. And we know that, right? Okay, on this page you have more practice. I'm going to let you do that in a minute, but what I would like to do is I would like to talk about how we can recognize and utilize matrices in a word problem. So here's a beautiful application problem. Okay, so you have practice there, but then you also have on my math lab, right? Application, matrix multiplication. Suppose that the dance concert at EHS will be performed on 3 different evenings. So I see 3 evenings. Opening night, second night, final night. The expected attendance for each evening is shown below. The adult tickets sell for $5. So I'm just going to tell myself those are $5. And the students' tickets sell for $4. So I have some data here. You are to use matrix multiplication to determine how much money will be taken in each night. Now, I don't have to use matrices, but you're being asked to use matrices. So what I would do is I would first represent this data here in a matrix. And what is the order of this matrix? It is a 3 by 2 matrix. Now I know the cost of each of these. So I know that I'm going to multiply by the cost to get my total amounts for each night. Now let's think about this. Does anybody have any ideas? It is going to be a 2 by 1, right? For us to even be able to perform this. And the resulting matrix is going to be a 3 by 1, which is going to have in every row the amount I would make for each night. Now, I know that this has to be multiplied by $5. So to get this, I'm multiplying first row, right? First, yes.
I get like you put it so that let's say the first matrix is 2 by 3. Yeah, that doesn't make sense.
Then it would be a 3 by 1.
Yeah. So
right? We'd have 3 prices.
We can change the second matrix.
Yeah. 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 Well, I mean, we'd have to have the data to be able to put in the matrix to be able to answer the question, right? But I could have easily told you there's 3 prices, but then I'd have another column in the first matrix and another row in the second matrix. But do you see, to get this, I am multiplying this by this by this, right? So $5 for every 420 tickets sold, $4 for every $300 ticket sold. So how much did I make the first night? And doesn't that make sense? Yeah. Okay, what about second night? How much did I make the second night? And what about the third night? Mm-hmm. 510 times 5, 475 times 4. I mean, you have calculators, right? You technically should be able to perform that multiplication and addition, but if you didn't, 4,450. So I technically could ask you a lot of things. I could ask you how much was made each night. You'd say on the first night I made 3,300. On the second night I made 3,800. On the third night I made that. Or I could ask you how much did I make for all 3 nights. You'd add those together, right? Okay. Now, there's a couple of more things that I want to talk about. Remember that the additive inverse is, what are you adding to something to get 0? Right? What am I getting to get 0? Versus the additive identity, which is 0 matrix. So we kind of need to know the difference between these two. The additive identity is the 0 matrix. The additive inverse is the opposite of every single element. So the opposite of A is negative A, and you would just negate each of these, because if I were to add A and negative A, I would get the 0 matrix. So you need to know the difference between these two. Multiplicative identity is just the identity matrix. It's like multiplying by 1. And what matrix can you multiply and not change the original matrix? What can you multiply? The identity matrix has 1s on the main diagonal. Oops, I just erased it. 1s on the main diagonal and 0s everywhere else. So this is the multiplicative identity. It's known as the identity matrix for a 3 by 3. The identity matrix for a 2 by 2 is this. The identity, and I could just write the single number, or I could write 2 by 2. Those mean the same thing. Now, the last thing I want to tell you is that your calculator can perform matrix multiplication and matrix addition and matrix subtraction. So shall we look at that ever so quickly? Let's pull out our calculators and let's talk about how to perform matrix addition, subtraction, and multiplication. We know how to put in a matrix, right? We know, we did that yesterday. We can put the matrix into the calculator. The question is, how do we get the calculator to actually perform the operations? So I'm going to go to, let's clear everything, and let's go to second matrix. Let me just see what I got in there. I got a 3 by 4 in there. So let's say I want to edit and I want to add another matrix. And I'm going to say, let's add a matrix that is a, well, what order matrix could I add to a 3 by 4? What could I add? It has to be a 3 by 4, right? Same order to add or subtract. So I'm just, for kicks, I'm just throwing this random, I mean, it doesn't matter. I'm just going to do this. okay? It doesn't matter what the entries are. It's just to prove that I show you how it's done, okay? So there I have another matrix. For kicks, what's another matrix? What's the order of a matrix that I would have to add to input to multiply by this? Okay, 4 by 3, or, you know, let me just say a 4 by 1, so I don't have to enter in so many elements, right? Okay, so I have these matrices. Let's talk about how to perform matrix operations. So if I want to add a matrix, let me call up matrix A, and I'm going to add matrix B. I should be able to add those. There I go. What if I said matrix A plus matrix C? We know that can't be done, right? Ah, look at that. See, the dimensions of the matrices are not the same. So it's telling you the error. So don't come to me and say, oh, I got an error. Well, you need to be able to interpret that error. Okay, let's talk about matrix multiplication. I know I can multiply A by C. There it is. I knew that was the order. Can I multiply C by A? No. Look at that. See? So you can check your answers right now. Needless to say, you'll have to do all of this by hand on the quiz, right? You're not going to be doing any operations on the calculator. Yes, sir.
How do I get an error for 3 by 4 and 4 by?
Yeah, you need to go and make sure everything else is off, right? So I mean, come back.
Someone like
Uh-oh. Well, we need to make sure all our plots are off. We can come over here and make sure. I would just get rid of everything, right? So there you have it. Now try those matrix multiplications, the ones we skipped. Go back to the previous page and do those 3 real quick. They're real tiny. And let's see if we get the same answer. No, by hand. And check them on the calculator. Why do them on the calculator to start with? So you can miss them on the quiz next week and then we all upset. Yeah, let's do them by hand. So we're doing them by hand. Well, I have to see what's going on. Come here and let me see what's going on.
I don't know. I think, do I have to do that Windows thing?
No. Okay, so let me see your matrices. You want to multiply A by B?
Yeah.
Multiply A by B, right?
I put add.
You can't add those. Those aren't the same dimensions. Oh my goodness. We just said they have to be the same order. I get, that's what happens when you take your mask down off your nose. Okay, so we're doing the 3 problems we skipped. Check them on the calculator. Check them on the calculator. You should be able to get them. Did you get it now? Oh my goodness. And what does that mean? Y'all tell him what that means. What does that mean?
But it's 3 by 4 and 4 by 1, so it should work, right?
Are you multiplying?
It's multiplying. 4 by 1.
What order are you doing? What order are you doing them?
A times B.
Okay, A times B, 3 by 4 and 4 by 1 would work.
Yeah.
Okay. But B times A ain't gonna work.
Yeah, but I have A times B.
So you should be able to check these in the calculator. I gotta see what's going on. Let me see the error. Well, why are you doing RREF? We're not finding the reduced row echelon form. We're not doing row operations. We're just performing matrix operations. That's where you're going wrong. Okay, you should be able to check these in the calculator. Can I perform the first operation, A times B on that problem? Can I do that? Yes, no, maybe so. Can I perform the first operation? Yes. You should be able to get the first operation. You can do A times B, 2 by 2 and a 2 by 2. These are the same, so my result is a 2 by 2. Can I perform the second one? Yes, I can. These are the same, so my answer is a 2 by 2. Can I perform the third one? No, because these are not the same. So I can't multiply those. And of course, you would always tell me why. On the page right before the... Okay, any questions of those of you who are not in the room? Are we excited? Okay, so we got a lot of homework to do, right? Chill out on the homework. No joke. You gotta practice makes perfect. Okay. Y'all have a lot.